Assalamualaikum warahmatullahi wabarakatuh. My name is Isur Hizami Ali. My metric number is 231110917. Today, I would like to talk about topic 4-6, which is the Reynolds transport theorem. First thing first, we will see what's the example that the slideshow has given to us. It shows that the two methods of analyzing the spray of deodorant from a spray can. We can they give us two ways. The first one is we follow the fluid as it moves and deform. This system is this is the system approach. No mass cross the boundary and the total mass of the system remain fixed. The second way is that we show the second method to analyze the spraying of deodorant can is we can consider the fixed interior volume of the can. This is called control volume approach. So based on how do we know about the two methods, how can both of these methods be interact with each other? Well, that is where Reynolds transport theorem come from, which is RTT for the short form. The relationship between time rates of change and expense property for a property system of control volume is expressed by RTT transport. Now we will see how it is representing in a graph. This is a formula that we will use to calculate the RTT method, Reynolds transfer theorem. Based on the given diagram, we can see that the purple graph is the outflow during the delta t, and the green one, which is the control volume or inflow during delta t. This means the Reynolds transfer theorem is this part, in between those two, which is its system at the time t plus delta t. The rate of change of this property B of the system is equal to the time rate of change B of the control volume plus the net flux of B out of control volume by mass crossing the surface. This equation apply at an instant time where it assumes the system and the control volume occupy the same space at the particular instant in time. Meaning we doesn't calculate meaning we only calculate the instant at one particular time, not more than that. Like what I said earlier, a moving system had, which is the hatches region, and the fixed control volume, which is the shaded region, in a divergent portion of a flow field at time t and t plus delta t, the upper and lower boundary of the streamline of the flow. Now let's continue. Uh, we will see to B is representative of any exclusive property such as mass, energy, momentum, and much more. Then small b is equal to big B over M is representative of intrinsic property. Nothing that extensive property are additive. The extensive property B of the system at time t and t plus delta t is expressed as B system t equal to B control volume t. This system and control volume considered at time t. Next, we can expand the equation by make it becoming this equation. Then we will subtract the first equation to the second equation and divide it by delta t. We will get this equation. Next, we will take the limit of delta t to 0 using the definition of the derivative, and we will get the equation that we want, which is dB system over dt equal to dB control volume divided by dt minus B in plus B out. Additionally, B in and B out. Additionally, B can also be equal to B rho VA. This can become this equation. And since we know that B, since we know B uh, T plus delta T equal to Bm plus delta T equal to this equation, we will get B delta T, B rho V delta T A. We can do the same for B1 and B2. And we will achieve the final equation is this. That is what we will get if we get the control volume at a specific control volume and system on the same size. Next, we will look at RTT when derived by control volume. This meaning there's only one mass entering, but two mass leaving. First, this is the equation of the type of question, which is B net equal to B out minus B in. So this will be the equation for this type of integral. B net equal to B out minus B in equal to integrate rho BV dot n. The integral of B rho V dot n dA over the control surface given the net amount of property B flow out of the control volume into the volume if it's negative per unit time. So B control volume will equal to integrate rho B dV, which will be based on the control volume. Now, how do we know whether it is outflow or inflow? That won't be easy. We will look at the delta. If the delta is less than 90 degree, meaning it is an outflow. If delta is if delta is more than 90 degree, it will be inflow. Next, we will see that the outflow and inflow of mass across the different area of control surface. This equation will be used if this Reynolds transfer theorem equation will be used if we get a fixed control volume, which is we just plus it. We just need to add plus with another rho BV dot n dA. Objectively, we can also use this equation if we got another fixed CV. Relative velocity of this type of situation will be RV equal to V dot V for the control volume. RV, this is the equation if the Reynolds transfer theorem is not a fixed control volume, and this is the equation if the Reynolds transfer theorem is a steady flow. Reynolds transfer theorem apply to control volume moving at a constant velocity. Relative velocity crossing a control surface is founded by vector addition of the absolute velocity of the fluid and the negative of the local velocity of the control surface. Next, we will see the approximate of RTT for well-defined inlet and outlet will equal to this. Finally, we will get the approximate RTT. The next equation that we will use will be this equation, which is the dB system over dt equal to dt integral rho b dv plus delta out minus in. And next, finally, we will see the approximate rotation transport theorem for a well-defined inlet and outlet will be dB system over dt equal to d over dt integral limited by control volume rho b dv plus this one plus this equation. An example of control volume in which there is no well-defined intent and 1, intent 2, and 3 flow surface in RTT can be more convenient right in terms of average value of fluid property crossing each outlet. That's it from me. Thank you.